Today I'm just going to recap some of the key ideas that we've looked at in the previous few lessons, and this is mainly to do with how we can manipulate a right-angled triangle. So here I have drawn a right-angled triangle, and the first thing we've looked at is something called Pythagoras Theorem, and we stated that on a right-angled triangle, if we have a hypotenuse of C and two side lengths of A and B, we managed to deduce that a relationship between these three sides would be that A squared plus B squared equals C squared. That means that if we had the two shorter sides of a right-angled triangle, so let me just draw one here. If we had two shorter sides, let's say there were 3 and 4 respectively, we could use this formula to work out what the hypotenuse would be. From this, we would know that 3 squared plus 4 squared must be equal to x squared. Work out what 3 squared is, which is 9. 4 squared, which is 16. Therefore, my value of x squared must be equal to, well, 9 plus 16 is 25. To get the value of x then from that, we need to square root 25. Which would give us two answers, positive and negative 5. However, we know that we're looking at an actual length. It's a real life thing, so it would be really silly of us to think that a negative 5 would be a real life length. So we would state that x has a length of 5, and let's say all of these are in meters, so x would be 5 meters. The other scenario that we could have is if we had a right-angled triangle, and let's say it had a hypotenuse of 13, and a side length of 5, how could we work out this missing side length? Now, I showed us two ways we could do this. The most common way that we did was we'd recognise that we had a hypotenuse and a shorter side. So we can manipulate this to find the shorter side by subtracting, let's say subtracting b squared across. We would get that c squared subtract b squared equals a squared, and we would then use this formula, this second formula, for this triangle here. So 13 squared subtract 5 squared would give me x squared, if I labelled them as c, and then this would be b, and this would be a. 13 squared is 169, 5 squared is 25, and x squared remains the same. So that would give me x squared as a value of 144, so therefore, x must be equal to the square root of that, and I would always write this square root step first, because this could help us when we do multi-step Pythagoras, which would give us an answer of 12. Okay, so that was Pythagoras, so make some notes on that. However, what we came to look at in the most recent lesson we've done is still looking at a right-angled triangle, but this time I told us some information about an angle as well. So Pythagoras only works if we have all three sides. If we have an angle involved, let's call this angle theta, and we have a right angle, we had to do something else, and what I told us we could do was, first of all, we could label our triangle differently. Now we have some specific words that we use for this. We say that the line, which is opposite the right angle, we call that the hypotenuse. It's the longest line. It's also what we called it when we did Pythagoras. That is called the hypotenuse. So I'm just going to write this as a H, Y, and a P, and that's my hypotenuse of a triangle. The next thing I look at, typically, when labelling a triangle, would be what is in relation to this angle here. And again, if we look at the side opposite this angle, we would call this the opposite, because that's just what it is. It's opposite the angle. And the last one we look at is if we have a side length which is next to or on the same line as our angle. This is called the adjacent, because adjacent just means next to. So I'm just going to call this ADJ. Now, what we explored and what we discovered in lessons is that when we look at the ratios between these side lengths, they remain a constant if the angle is the same. Doesn't matter on the size of a triangle, if they had similar triangles, the ratio between these side lengths would stay the same. In order to write this, we came up with some words. We said that the ratio between the opposite and the hypotenuse, we call this the sine ratio. So depending on what this angle theta is, the opposite and the hypotenuse will always have the same ratio. Likewise, when we looked at the adjacent and the hypotenuse, when I divided these together, I ended up with a different ratio, and it was the cosine of theta. And typically we just simplify this to be cos for short, and that's how the calculator shows it as well. We looked at why this is the cosine, because we thought if we had this angle theta here, if we drew on theta prime, which would be 90 subtract theta, we would have the same triangle and it would be a complementary angle. However, we don't need to go into much detail on that at the moment. We are just trying to think about our properties of our ratios. So we've got sine is opposite over hypotenuse. Our cosine or cos is our adjacent over hypotenuse. The last one to think about would be my opposite over my adjacent. And we call that the tangent. And again, these are things that we're going to explore further on in the curriculum. We call that the tangent, or tan for short. So, from here, what we looked at was what scenarios happen looking at these values. So, if I just draw a scenario here, and I say we have an angle, let's call it 60 degrees, and we have a hypotenuse, which I want to find out, and an angle over here, a side length over here, let's call it 15. I would like to use this triangle to work out the hypotenuse. So to do this, the first thing that I'm going to do is label my triangle. So I have the opposite, I have the hypotenuse, and I have the adjacent. I've just abbreviated it even further because as mathematicians we are notoriously lazy, to be O, H and A, and I'm going to look at what I have. I have information for my opposite and information for my hypotenuse. So if I scroll up, I'm looking for something which relates my opposite and my hypotenuse, and that would be this sine theta. So I'm just going to write it down in full. I'm going to write down that sine of theta is equal to my opposite over my hypotenuse, and I'm going to substitute in every value that I have. I have the sine of 60 is going to be equal to my opposite, which is 15, over my hypotenuse, which is x. And I want to think about how I can manipulate this to get x on its own. So, looking at this, what I showed us in lesson was looking at a similar example. I think I said if 2 is equal to 16 divided by 8, then we could look at our division laws to notice that 8 is 16 divided by 2. I can swap these two values around and it would still be equivalent. This is really important because for this example now, if I swap my x and my sine 60 around, I end up with x equals 15 divided by sine 60. Then all we do is we go on a calculator, we write 15 divided by sine 60, make sure you close your brackets, and you end up with an answer of 17.32. And it goes on a little bit. That's one example. As I go down, I'm going to show you another example. Again, it's going to be a right angle triangle because that's all we're looking at the moment. And let's say I have an angle here of 50 degrees. And let's say I've got a side length of 10 and a side length of, well, if this is 10, this is going to be 12, let's say. Oops. Let's not do that. Let's say that this is x. Okay. I'm going to do the same thing now. I always start off with labeling my sides, and I start off with my hypotenuse, then my opposite, and then my adjacent. I look at this and I think, what values do I have? I have information for my adjacent and information for my opposite. So to do this, I'm going to think about which of my trig ratios gives me information for my adjacent and my opposite, and it would be tan here. So therefore, scrolling down, I will know that tan theta is equal to my opposite over my adjacent. Same steps now, I'm going to substitute in what I know. Tan of 50 is going to be equal to my opposite, which is x, over my adjacent, which is 10. And again, I've got the same scenario as I had in my previous example with sine. I have some value of sine, or tan, is equal to some fraction. But this time, we should note that my missing value, my variable, what I'm trying to find, that x, is on the numerator of a fraction. So therefore, what's happening to x is I'm being divided by 10. To counteract that, what I'm going to do is I'm going to multiply both sides by 10 as I go down. So therefore, I end up with 10 lots of tan 50. And that's going to give me a value of x. So I work that out on my calculator. Sorry about that. 10 times tan 50. And I get a value of x to be 11.9175. So 11.92, roughly. These would be two examples of how we can look at the trigonometric ratios. So if you need any further help, please let me know. However, thank you for watching this video.